A dark strip of freshly cut asphalt cuts across the city lane, hiding a thick ring of copper wire buried just inches below the road surface. Most drivers roll right over these thin, black rectangles every single day, without ever knowing they are there. Yet these silent wires act as the primary eyes and ears of modern urban roads, constantly watching every single vehicle that approaches a red light day and night. The science behind this clever system rests on a simple law of electricity and magnetic fields discovered long ago by 19th century scientists. An electrical current flows continuously through the buried wire coil, turning it into a silent magnetic trap that fills the space directly above the asphalt. When a heavy steel vehicle rolls over the buried wire loop, its large metal frame changes that invisible magnetic field instantly. That sudden shift in the magnetic field changes the overall electrical inductance of the buried wire loop circuit. Inside a nearby metal cabinet standing on the concrete sidewalk, a small sensor circuit detects this sudden drop in electrical balance within a few milliseconds. The system knows instantly that a car has arrived, counting the metal weight resting above the hidden wire ring without needing any visual camera lenses or moving parts. Before these buried copper rings became standard across major cities in the middle of the 20th century, urban roads relied on simple mechanical switches or rigid clock timers. In the 1960s, as millions of new passenger automobiles flooded suburban streets, city planners needed a tougher system that would not break down under heavy truck tires or freezing winter weather. Sawing thin rectangular slots directly into cold street pavement turned out to be the ultimate lasting answer. Fixed clock timers were a constant nightmare for city drivers stuck waiting at empty street corners late at night. A simple mechanical clock would hold a red light for 2 full minutes, even if no cars were traveling along the cross street. Drivers wasted expensive gasoline and lost patience while staring at empty pavement, proving that rigid time slots could never handle the true chaotic rhythm of modern urban vehicle transportation. Inductive loops changed everything by giving each individual intersection a real-time voice to call for green lights when cars arrived. The small copper loop sends a low electrical signal along insulated cables running straight into a gray traffic controller cabinet standing on the curb. Inside that roadside locker, specialized circuit boards read the incoming signal and decide if a waiting driver has stayed long enough to earn a green light. When multiple cars line up in a single turning lane, the hidden loop senses the prolonged disruption in its surrounding magnetic field. If the cars keep rolling past one after another, the loop registers continuous occupancy, telling the roadside controller brain that heavy traffic is building up rapidly. The controller extends the green signal for a few extra seconds, allowing the line of cars to clear out smoothly before changing back to red. By placing 2 separate wire loops a precise distance apart in the same travel lane, the local traffic controller learns even more about the road. It measures the precise millisecond delay between the moment a vehicle triggers the first wire ring and the moment it triggers the second ring. With basic mathematical formulas, the controller instantly determines the exact speed of every passing automobile down to the single mile per hour. Speed detection allows local traffic networks to spot sudden slowdowns or unexpected highway crashes long before a human driver calls for emergency help. If cars suddenly cover both wire loops at the same time and stop moving completely, the system recognizes a severe bottleneck. The controller stops giving extra green time to that blocked lane, preventing an endless line of vehicles from spilling backward into adjacent cross streets. Individual intersections working on their own can only do so much to fix heavy traffic jams across a sprawling modern metropolitan area. When every street corner makes choices isolated from its neighbors, a green light at one block might just push a wave of 100 cars directly into a red light at the very next block. To solve this urban puzzle, engineers connected thousands of local controller cabinets into giant wide-area networks. In the late 1970s, traffic engineers in Australia created a groundbreaking central computer network known around the world as SCATS, short for the Sydney Coordinated Adaptive Traffic System. Instead of letting each streetlight act alone on fixed timers, SCATS gathered real-time loop data from hundreds of key intersections at once. This central software brain calculated real traffic demand across entire city suburbs in a matter of seconds. Under the SCATS system, the central computer constantly monitors how full each buried wire loop is during every second of the day. If a main highway entering the city gets packed during morning rush hour, SCATS automatically shifts signal timing along the whole route. It stretches green lights into long green waves, pulling thousands of commuters through the city grid without requiring a single manual adjustment from human operators in a control room. This automated coordination saves city drivers millions of hours in wasted commute time every year and dramatically cuts down on urban air pollution. By reducing the constant stop-and-go movement of heavy delivery trucks and private cars, loop sensors lower fuel consumption and dangerous exhaust fumes in dense neighborhood streets. The quiet dance of buried wire coils transforms chaotic traffic grids into a predictable, smooth, liquid flow of human movement. Installing these buried copper rings requires careful work from specialized road crews, who often operate during late-night hours to avoid daytime traffic. Workers use heavy diamond saw blades to cut thin rectangular channels directly into the asphalt before laying down several turns of insulated copper wire inside the groove. They pour thick black epoxy sealant over the wire to protect it from rain, road salt, freezing ice, and heavy truck tires. Despite their durable design, buried loops face serious risks from constant heavy wear and tear on busy city thoroughfares. Over years of scorching summer heat and freezing winter ground frost, expanding asphalt can crack the thin protective insulation around the copper wire. Water slips into the shallow cut, shorting out the electrical current and causing the local controller to think a car is permanently parked above the sensor. When a loop circuit breaks open or shorts out, the local controller defaults to a safe fail mode routine to prevent total urban gridlock. It may give short green lights to that lane on a rigid backup timer or keep the green light running longer than necessary to prevent traffic backups. Road crews must hunt down these invisible wire breaks using special electrical testing meters before repaving the damaged street section with fresh black asphalt. Over the past 2 decades, new traffic sensing technologies like optical video cameras and radar units have appeared on tall light poles above the street. These overhead eyes can spot vehicles without needing road workers to cut holes in the hot asphalt below. Yet camera lenses can easily get blinded by bright glare from the morning sun, heavy, thick fog, driving rainstorms, or blinding winter snow cover. Because buried inductive loops sit safely below the road surface, they remain completely unaffected by bad weather or poor visibility conditions. Rain, snow, fog, and pitch-black darkness cannot hide a heavy metal car frame from the invisible magnetic field created by the buried copper ring. This total physical reliability is why city engineers still rely on buried wire loops as their foundational sensor choice for critical urban intersections. Modern inductive loop design has also adapted over time to detect smaller metal objects like motorcycles, lightweight bicycles, and electric scooters. Engineers wind the buried wire into special diagonal patterns, such as a quadruplex figure-8 loop, which boosts the magnetic sensitivity along the center of the travel lane. Small aluminum wheel rims that once went completely unnoticed now trigger green lights just as reliably as heavy pickup trucks. As modern cities transition toward connected self-driving cars and smart road infrastructure, the humble inductive loop remains vital to traffic management. These buried wire networks provide ground truth physical data that validates overhead camera feeds and digital vehicle tracking applications. The precise count of metal frames rolling over road asphalt gives urban planners accurate real-time counts needed for future highway expansion projects. Every smooth green light wave running through a busy downtown core relies on these simple wire rings buried under the dark pavement. The unseen dialogue between copper loops, local controller cabinets, and adaptive systems like SCATS keeps modern society moving forward without constant human oversight. Without these quiet magnetic gatekeepers watching every corner, modern urban centers would quickly grind to a complete standstill under the weight of millions of cars. In the end, the ultimate success of city traffic control comes down to a simple coil of wire buried inches below our vehicle tires. As millions of commuters head home tonight, they will glide through automated green signals guided by an invisible magnetic network beneath the street. It stands as a quiet engineering masterpiece, operating silently below the surface, mastering the chaotic pulse of the modern city block by block.